I'm going to get into the architecture of Milvus a little bit. We're going to talk a little bit through what makes a distributed system database special and what it helps you do. And then I'm going to talk a little bit about Zilliz Cloud, which is a fully managed version of Milvus that also has some sort of hardware optimizations built in. And then I'm going to advertise Zilliz Cloud to you a little bit, talking about who our customers are, what they're working with. And I'll put some time at the end to let you guys ask any questions that you want. So let me get started here. Let's share screen. Here we go. Ooh, okay. Can everyone see this? Everyone can see this? Okay. Looks like we got a small audience here today. So I guess this gives us a chance to do a little bit more of interactive session. So if you guys could, I'd love to see, I'd love to have you guys drop in the chat if you're a software engineer or a data scientist or whatever your role is, so that it'll help me more angle this towards something that'll be helpful for you. Okay, so software engineer, good, good, okay. Okay, software engineers, okay, good. So it looks like that we have a pretty strong engineering audience, and that's great because this lets me talk about Milvus and the infrastructure of Milvus and stuff like that I really like. Oh, we have someone in sales too. Okay, good, good. So you're in sales. Everyone is just messaging the hosts and panelists. That's why I see all of the messages, and that's why I'm reading them out loud, because I know that you guys can't see them. LOL. Yeah, see, I can see everything you're typing. Okay, cool. So I'll talk a little bit about the sales side of things, but at the beginning, we're going to focus on some of the architecture and engineering stuff. Okay, product and engineering. Cool, cool. So yeah, I'll cover product, but we're going to start with the engineering stuff. This is what I think is the most interesting part about Milvus. There's no introduction slide about me here. Usually there is. So I'll kind of cover that right now as well. So my name is Yujin Tang. I'm a developer advocate here at Zilliz. I come from a software engineering background. Prior to being at Zilliz, I've run a natural language processing API that I created myself. Drove about 2.5 million at Amazon in slightly under a year. And I started working at IBM when I was 16, and I've published 2 different first author papers on machine learning. So yeah, very heavy machine learning background, and this is I think that what we're doing with vector databases is going to be one of the most important pieces of the new LLM kind of paradigm. So let's start with why we are building Milvus like this. Why does it matter that Milvus is a distributed system vector database? So right now, the way that I understand how other people see vector database from the outside is that people are looking at vector databases and they're like, this is the same thing. This is one blob, right? It's a vector database. But in reality, the implementation of the vector databases are very different. At their functionality level, all vector databases do this thing where they do similarity search. But for us, Milvus is a vector database that is built with one goal in mind, and that goal is how do we handle insane scale? How do we handle ridiculous scale? Alibaba has 5 trillion vectors, and that is our goal, is to be able to handle that kind of scale within the next few years. And the reason why we believe this is so important, the reason why we believe that handling scale is going to be the most important problem to solve in this space, is because inherently vectors are ways that you can represent unstructured data. And this means that vectors are going to be used to represent more than 80% of the data out there, right? I'm sure you guys have seen the Gartner stuff, all of these market research things that say 80% of the data that we have out there is unstructured data. And so what this means is that there's 4 times more data out there that isn't being analyzed, isn't being used right now, than there is data that is being used, right? We're literally only touching 20% of the data that we estimate to be out there. And we're not even analyzing and using all of that. You know, if you were at a company, actually, this would be great to get some some input from the audience as well, is if you work at a company, does your company leverage all their data? Does your company use all of its data, or is a lot of your data just sitting there? You know, let me know. I'm going to continue talking, but, you know, let me know and I'll comment on it as I see it, right? So my guess is that your company probably doesn't use all the data out there, right? So let's talk a little bit about Milvis's architecture and why this is something that allows us to build something that's going to scale. So this is a high-level overview, a high-level diagram of what Milvis's architecture looks like. I'm going to start with an SDK. We have two core SDKs. This can you clarify, the scalability target, is that for Milvis or Zilliz? Right. So I will go into this just a little bit later. Milvis is the open source, commercially available, you can use it for free option. And our goal is for Milvis to be able to support this, whatever it is, whatever scale needs to be supported, trillions of vectors. We want Milvis to easily support that. Zilliz is our commercial offering of Milvis. It is our cloud managed, fully managed option for you. And I always tell people, so my role here at Zilliz is to get people to use Milvis, is to get people to use vector databases and teach people about Milvis, because Milvis is really, really, I mean, at least in my opinion, it is extremely innovative. And whoever built it, I mean, like the team that built it was really, really thoughtful in how they approached this. And if you've seen the architecture for SQL databases, for NoSQL databases, you will understand what I mean when I say this is an innovative architecture. But Zilliz is obviously our commercial offering. We are a business, so we would like to move people to Zilliz. And I tell people, you should use Milvis until you don't want to handle the DevOps anymore. And once you don't want to handle the DevOps, you should go to Zilliz. Because, you know, for most companies, like, is handling the DevOps really a core part of your business? Is it mission critical for you? And if it is, then, you know, handle the DevOps yourself. You know, we provide Milvis with a commercially free option for that we allow you to do that, right? But if handling DevOps is not mission critical to you, if it doesn't generate revenue for you, then you should use Zilliz, because it's probably going to be cheaper. You're probably going to have to pay less DevOps engineers. You probably have to pay less DevOps costs, because vectors are a very intensive, very computationally intensive data type. And so working with these, you have to be able to optimize your EC2 instances and other things like that. And so if you don't want to do that, that's where Zilliz really comes in. H. Kraus, how does the Zilliz service integrate with on-prem or cloud platforms like AWS? So we are on AWS Marketplace. So you can integrate with Zilliz directly on AWS Marketplace. For on-prem, there is one, I actually don't know if this is out yet. This is kind of embarrassing. I think this is out. We offer a service that lets you maintain the data plane, and we only maintain we only touch the control plane. So we never touch your data. We never see your data. This is something that I know that a lot of security-oriented companies are very interested in and very, you know, much want to do. And so this is something that we are offering. It may be available now. It may not be available for the public, but it is definitely available for enterprises. So if this is something, if the on-prem option is something that matters to you, then you know, I would suggest getting in touch with the team here and talking about that in more detail that way. Okay, so let's talk about the architecture. So Milvis is the core features, the core design decisions here are revolving around how do we build a system that will allow flexible scaling and make it easy for you to not have to do things like data migrations and to reduce the amount of computationally intensive tasks that you have to do with the system. And this is different than the design decisions that go into a SQL or a NoSQL database, because SQL databases, for example, SQL databases require more complex operations across different tables. And this is because the meaning behind the data in SQL databases is spread across these tables, right? You have relational, that's why they're called relational databases, right? They match IDs and they match parameters with these IDs or attributes with these IDs, and that's how they determine the meaning behind the data in the database. A vector database is very different because vectors encode nearly all of the semantic meaning that you need, and you can add metadata to it, and you should add metadata to it. It will enrich your data, and it will make the search experience better for you. Milvus allows filtering, and so the primary thing here is you do not have to connect databases. The complexity of queries is limited to row specific operations, which means we only need ACID at the row level. And the way that we model this so that this is possible is that we model the entirety of Milvus, the entirety of the data operations in Milvus anyway. We model the entirety of the data operations in Milvus as a publishing as a pub sub service. You're publishing data to basically Kafka, through Pulsar, through some sort of stream, and then the data node will subscribe to that, and they will read that, and that is how that will get in there. And so that actually allows a functional, that allows decoupling of basically every function in the system, as long as it is not within the same functionality, basically. So the way we do this is we have a set of, you'll see at the bottom here, we have the set of worker nodes. These worker nodes are stateless. These are just nodes. These are essentially like CPUs, so you spin up whenever you want. On top of that, the way that we work with these worker nodes is we have a coordinator service. And the coordinator service essentially tells the nodes what to do. And in order to store the data, we have object storage such as MinIO, S3, blob storage, whatever it is that you need. The reason why this is so important is because this architecture, this design, allows us to orchestrate a true separation of concerns. When you're building a search system, when you're building something that is focused on searching at scale, you really have three separate concerns. One is, how do I query my data? Two is, how do I get my data? How do I put my data into storage? And three is, how do I access my data? And so this, for us, we separate these into query, data, and index. And these nodes are all these functionalities need to be decoupled and need to be separate from each other because they're going to be used differently. The query node is going to be used to query, right? It's going to be used to find your data in the system. It's going to be used to grab your data. And grabbing your data has nothing to do with you putting your data into the system. And so the data node and the query node have to be decoupled. And the index node here also has to be decoupled because using something to create a way to access your data has nothing to do with whether or not the data is coming in. It has nothing to do with whether or not you're asking for specific data. So all three of these concerns need to be separate from each other. And so that's why we have these decoupled functionalities. And then on top of that, we have this this concept of allowing you to write and keep your data consistent, right? One of the most difficult problems to deal with a system that is constantly updating is this data consistency. How do I make sure that my data is the most recent data, or at least the most acceptable recent data? And one of the issues with building something that is not a distributed system, with building a single instance scale up, is you run into hardware problems. So for example, let's say you have, I'm not going to name any names here, but there are competitor companies that do this. And let's say that you are using one of those and you are on a single instance and you're scaling up, and suddenly you're hitting your 128 gigabytes of RAM. I don't even know if that's like, I don't know how big these can really scale up to, but like, let's say you're at 128 gigabytes of RAM, 256 gigabytes of RAM. Well, what happens then? What happens when you need to scale past that? You need to do a data migration. And so we abstract this out completely and we say there's no reason that you should have to do that, because we think that the main issue to solve is scale. So we want to make it easy for you to put your data in and to keep your data in there and to keep growing the amount of data that you have. And we want to make it easier to do that without having to do things like reindexing or data migrations, right? When you're doing data migrations, you have to worry about data consistency between your new data your old data. Where is the new data that comes in getting written to? Is it getting written to the old data? Is it getting written to the new data? Where is that getting written to? And where am I pulling the data from? Am I pulling the old data? Am I pulling the new data? When should I pull this kind of data, right? So data migrations, like I know as a software engineer at Amazon, I've seen this kind of stuff. Data migrations are not something that I want to do anyway. And so this is one of the things that we had in mind when we designed the system. And that's why, and that's exactly why we have this kind of stateless worker nodes that just store your data in object storage and are able to grab read-only versions and work with that. And that's why we have these index nodes that do this thing where you're building these indexes over segments. So index nodes we build an index on your data every time there's a 512 megabyte segment. Every time you put 512 megabytes into the system. 512 megabytes is just a default number. It is not what you have to use. If you want 256 megabytes, if you want 1 gigabyte, entirely up to you, we can do that. That is a configurable aspect of the system. This is just what we suggest. And not only is this good because you don't have to reindex, right? Because every time you're adding data, all you're doing is just creating new indexes. You don't have to completely take down an index and make a bigger index, right? So one of the issues with single instance scale-ups is, let's say you hit 100 gigabytes of data, and maybe that's the limit of your whatever storage thing. And you want to add more data. Well, now you've got to have your data in 2 different places, and you've got to find a way to index that data. And indexing is a very computationally expensive task, because indexing, you have to actually go through and you have to go and do all these vector calculations. And vectors are very, very long series of numbers. Typically, we see vectors of hundreds or even like 1,000, 2,000 dimensions, right? So OpenAI's vector embeddings are 1536 dimensions. So yeah, like as you work with this, you're gonna have to work with very, very complex data. It looks like there's a lot of questions coming in right now. So let me answer the questions, and then if there are more questions about the architecture, I will answer the questions about the architecture, and then I will go on. So let's see. Where does an LLM integrate with this architecture? What is the API for calling into Milvus for something like a similarity search? And this architecture is the database system architecture. The LLM is really part of the RAG stuff, the retrieval augmented generation. And while that is one use case for vector databases that we see is very popular right now, that is not the only use case for vector databases. And for example, our original biggest customers were using us for product recommendation. And product recommendation has nothing to do with LLMs, has nothing to do with RAG. And then another use case for us is there's companies that are using us for like DNA molecule kind of search, generative, like I'm not actually entirely sure how that works, but they're doing something with like molecule structures. And that has nothing to do with LLMs either. And so LLMs don't actually, like, we are not touching the non-database system aspect, because we believe that the database system itself is complex enough that you should focus on how do we provide the best database system. And similarity search is, well, we have an SDK called PyMilvus that you can use, or you can go on Zilliz, and Zilliz.com has a lot of different examples on how you can integrate with, or how you can use the API. But at its core, it's the same as connecting to any server. If you've ever connected to some sort of server, you know that there's a host and there's a port. And you can turn this host port into a URI. And then typically you pass some sort of API token. And for us, that API token is a username password. And so you can interact with the API for Milvus the exact same way that you would interact with the API for any server-based system, right? Because Milvus is a server-side vector database. Milvus is something that sits on a server. And the reason for this is, once again, because we believe in scale. Does Milvus store all of its data in Delta Lake format? No. I believe it is actually Parquet. But I believe you can also mess with that format if you would like. I think Parquet is the default. But that's a good question, because I will take this back and see if there there are other ways to store the data as well. Answer live. It looks like there are 3 types of worker nodes, query data index. Can all of these scale out to multiple machines? Yes, all of these can scale out to multiple machines. And actually, but so each node essentially is a type of machine, is one machine. And the way that we actually do scale out is we do sharding. And so shards can sit, so you can have multiple shards if you would like. You can have 1, 2, 3, however many shards. And then we have something called a shard delegator or a shard leader. And what this does is this aggregates all the shards, and this keeps track of the localization of where all your data is. So you can have one query node, and this sits on the query node. So the query node can typically hold the shard, and then what happens is individual shards also have access to segments, and segments are the 512 megabyte segments that do the indexes. So the shards are what controls the scalability, and you can put shards onto multiple nodes. And it is not a one-to-one. You can do multiple if you would like, based on replications if you need for high availability or whatever it is that you want to do with that. It depends on your use case, but the answer is yes. All three of these are scalable, independently scalable, do not need to scale with each other. They are decoupled. Okay. Can you still query data that has not been indexed yet? That's a great question, and the answer is yes. Yes, you can. So we have this thing called we have this concept in Milvus called a growing segment. And a growing segment is data that comes in, it goes to the message store, and in the message store, it gets timestamped. And that's how consistency works. We work with this thing called delta consistency. And what that means is, well, I mean, there's strong consistency and there's eventual consistency, right? So eventual consistency is essentially, is a delta of infinity, and strong consistency is a delta of 0. So we timestamp all the data so that we know, how long before the query do we need the data. But as this data comes in, it's growing. It's in a growing segment. What happens is the query node and the data node keep track of this growing segment. And if you need to query, or when you query, the query node has access to your growing data. And depending on what the size of that growing segment is, we will either already have created an index for it. So once it hits 10% of the segment size, so in the example that I gave, the default example of 50 megabytes or so, we'll create an index on it so that it's faster to search that. But before that, it's just brute force search through those vectors. So the answer is yes, you can do that. Is this something we'd have to worry about if we ran Milvus in our own data centers? I need you to expand on this a little bit more. I'm not sure what this is referring to. What is the engine that runs Milvus? Is it Java based? Like Milvus is written on Go. Delta Lake is Parquet with the addition of a transaction log. That might be right. We do have a lot of logging, and we do essentially structure the entire system as a pub sub log service. Okay, cool. Looks like we got through all the questions there. If you would like to re-ask this question about is this something we'd have to worry about, I can answer that. But if there's no other questions about the architecture, I'm gonna move on to the next slide. If there are questions about the architecture, we could probably spend a few hours diving into this, as I just spent like an hour earlier on Monday diving into this, and literally just the sharding and segment stuff. Okay, so here's the more advertising kind of stuff that talks about Zilliz. Zilliz Cloud is the fully managed Milvus service, right? So we put some sort of AI ML toolkits on there. So this is where the question about LLMs kind of makes sense. So we do try to make it easy to be able to pipe in your data or pipe in your embeddings or stuff like that. And we have some partner companies that do this as well. And we have Milvus, which sits in the middle. And this is essentially the Zilliz Cloud offering, is this fully managed Milvus. And additionally to Milvus being fully managed, we are also optimizing the hardware capabilities. And I mean, you can do this yourself, but obviously we put a lot of people onto this. We have a lot of expertise in doing this. And we just recently, not recently, I guess, I don't know how, it depends on what you think is recent. But about March of this year, we began our NVIDIA integration, and we finished that up earlier this year. I'm not exactly sure when, but we finished up our NVIDIA integration, and now Milvus can run on hardware accelerated GPUs. And one of the reasons why we did this is because, once again, vectors are computationally expensive data types to work with, right? We're working with hundreds of numbers, and the way we compare them is, there's 3 basic ways to compare these vectors. And One is Euclidean or L2 norm, right? That's x squared plus y squared square root. Now, in our implementation, we get rid of the square root because the rank order, whether or not you square root, is going to be the same, right? X squared plus y squared is the same rank order as the square root. The other ways you can do this are inner product, which is a dot product, which is just, we multiply all the numbers and then we add them and check out what that looks like. And then the other one is cosine similarity, where we measure the angle between the different vectors. And all of these are something that requires you to run compute through the vectors. And so you need something that is able to efficiently, effectively, and accurately run that compute. And so that's why we did the GPU integrations. Other things that we provide with Zilliz on top of Milvus include that, the multi-tenancy, right? You can use AWS, you can use GCP, you can use Azure. I think you can use Zilliz Cloud as well. Yeah, so I think that's the self-hosted option. Yes. Okay, so this is on the slide. The self-hosted option is that if you are an enterprise and you have a lot of data and you don't want to manage it, then you come to us and you say, hey, we want you to manage our data, to manage our vector database, but we don't want to expose the data to you. And that's what I was talking about earlier with the control plane, data plane separation. And next year we'll have a truly on-prem deployment, but we do not have that at the current moment. And we're also we have a lot of security and compliance initiatives and security and compliance things. Actually, I think they're on here somewhere. Yep, here they are. SOC 2 Type 2 ISO 27001, role-based access control, data encryption, built-in failover, 3 nines of uptime, these kinds of things. We're probably working on 4 nines, 5 nines of uptime, right? You guys are all software engineers. You guys, not all of you, but many of you are software engineers. You understand the uptime stuff. Okay. Is there an article on Zilliz that explains how you choose between Euclidean dot product and cosine distance? I will link some YouTube videos of me talking about this. Whoa, what just happened? Oh, what is going on? What are you guys seeing here? Okay, I don't know what just happened to my laptop. No, what? I'm sorry, I'm having technical difficulties. What is going on? Okay, I will link some YouTube videos of these fundamentals on Zilliz, and hopefully those will be helpful. So I will put this in everybody. Here we go. So these are where I talk about, they're very quick videos. I just talked about what is L2, what is dot product, what is cosine, what are the different advantages of these, and I provide a visual that lets you see kind of what they look like. Does Zilliz have comparative information for Milvus compared to other vector DBs for things like architecture, features, scale, and performance? So we do have things for scale and performance for architecture. It's hard enough to get people to document their own code. It's very, very difficult to get people to document other people's code. So we do not have documentation for Chroma, Weaviate, Quadrant. And obviously nobody can see Pinecone's code, which is, part of the reason why part of the reason why I don't think Pinecone is going to be a truly competitive solution for us is because we believe in the open source ecosystem. We are very much about the open source ethos. We believe that open source software makes things better, and Pinecone is closed source, and so I don't even really, not a fan. But anyway, features, scale, performance. We do have something for that. Let me find that. Features are hard, but scale and performance, here you go. Okay, done. Okay. It's the and so much more than Milvus slides. We see slides. Okay, good. Okay, cool. Yeah, I was having technical difficulties, so thank you guys for verifying this. All right. Pinecone says that adding too much metadata can hinder retrieval performance. Can you talk about that for Milvus? So it's Milvus. Okay, so this is actually a really cool point about the way that Milvus handles metadata. So Milvus lets you choose which metadata fields you want back. So your retrieval, if you don't care about if you have like metadata fields that you want back specifically, then you can put them in there. But if you don't care, like you don't need them back, right? You don't need them. You don't need all the metadata for every query you're going to do. You're going to do many types. There's a very high likelihood that you're going to do very many different types of querying, and because you're going to be doing different many types, you don't need to get the same metadata every time back. One of the cool things about the way that Milvus does handle metadata is that you can filter on your metadata, and I believe that there are many ways to filter on metadata. We have a page somewhere that tells you about all of the expressions, and the way the metadata filtering is done in Milvus is, I think this is absolutely brilliant, is it's actually implemented with the bit mask. And so what that means is that, yes, you're going to get time additions for metadata filtering, but that time addition is going to be a near constant time addition, right? It's going to be so small compared to the time that it actually takes to do the computationally expensive tasks of doing the vector search. So that's how we handle metadata, and that's why Milvus is able to scale along those lines as well without having much of a performance difference for adding more and more metadata. Other features of Zilliz is we have an auto index. So if you guys have heard of Facebook AI similarity search, we've got one of the people who wrote like a ton of code for Face. Face is a way to essentially build your indexes, a framework to efficiently build your indexes and to query on them. And so Face is probably somewhere under the hood here, but we auto-index your data, so you don't have to choose the index. You don't have to think about the index type. With Milvus, you should think about the index type, and it's actually quite important that you use the right index type because different use cases will require different index types. So, for example, if you are doing product recommendations, you may be fine with not getting good recall. You may be fine with, say, hey, I want 100 things back, and as long as 30 of them or 40 of them are, close enough to what I need, like are actually 30 of the 100 that I get back are actually the closest 30 in the real data, that's good enough. And the reason why product recommendations can do that is because when you're building a product recommendation engine, it's very likely that you have products that are, you're selling, and people who want to buy things are going to click through, and they will click through multiple things because they can't find exactly what they need, but they find things that are similar. I do this on Amazon all the time. I'm scrolling on Amazon, I'm doing my online shopping. I'm like, oh yeah, okay, this is kind of close to what I want, but it's not exactly what I want. Let me go see what's similar, right? Now, Amazon doesn't use a vector database, but the idea is the same, right? Like eBay uses us, Walmart uses us. So if you're on eBay or if you're on Walmart and you're like, so let's say you're on eBay, you're like, I want a shiny Charizard, or I don't know, something like that, right? I want a shiny Charizard, but what I see is a shiny Blastoise or something. Well, let me see what's similar here, right? And then maybe of the collections you get back, you get a bunch of Pokemon cards that are all Pokemon cards, and they're all similar to Blastoise. And maybe none of them are Charizard, but you'll click through and you say, hey, this one's Blaziken. Oh, this is also a fire type. Oh, cool. The next one has Charizard, and you'll see it and you'll get it. So product recommendation people, they don't really care, right? But then maybe you're doing maybe you're working with DNA and you're working with molecule structures. And in that case, you probably want 100% recall. You want to make sure that everything you get back is the closest that is actually the closest that you get back. You want the actual accurate structures. But in that case, there's some things that you don't care about, right? You care about throughput, but maybe you don't care about like consistency levels. You can do eventual consistency. So there's a lot of customization that goes into building your vector database and using your vector database. And it really, really depends on your use case. And that's why Milvus has all of these different features built in. And that's why Zilliz the auto index will look at your data basically, and it will build the index for you based off of what the best index is for that data. On top of these things, we have a bunch of integrations, OpenAI, Cohere, et cetera, et cetera. We support data migration. Remember earlier I was talking about data migration, right? You got to put your data, you got new data, you got old data, you got to make sure they're consistent, right? So we support these consistency levels. We support you doing the data migration. And we have on-demand scaling. So you don't have to worry about on-demand like load balancing and scaling. So you don't have to worry about things like, oh, like tomorrow is let's say your eBay. Tomorrow is eBay day. I don't know if that's a real thing, but Amazon has their Prime Day, right? So tomorrow is eBay day, and we're expecting like 10 times traffic, so we need to scale up. Well, you don't need to do that with Zilliz, right? You don't need to have your DevOps engineers do that. You don't have to have your DevOps engineers build a prediction system. You can just say, okay, we're on Zilliz. Zilliz will scale it up automatically for you. On top of that, there's like a lot of monitoring, like log stuff. So we'll alert you to your usage. We'll tell you about, have you used this collection? Is it sitting empty? Are you using it a lot? Is it going over your desired budget, et cetera, and et cetera. Your architecture slide showed DDL, which means schema definition. How do you design the schema for a vector database such as Milvus? Wow, what a great question. So schema is okay. I think about schema design a little bit differently than the way that we as a company promote schema design. But I think that you should be defining your schema based off of the metadata that you need. You need an ID field and you need an embeddings field. You need the embeddings field so you can compare the vector embeddings across across the vector embeddings. And you need an ID field so that you can retrieve specific vectors, right? And then we introduced this feature recently called dynamic schema, which allows you to essentially just throw in JSON documents as long as you have an ID and an embedding field. We don't care what the other fields are. And the reason we do this is because we want to allow for flexibility in the data that you put in there, because as much as I think that all data schemas should be enforced, but in reality, that is not how people use things, right? You can tell people all you want, use it this way, but they're not going to listen to you. And so you have to be able to account for that and work around that and give people the tools they need to use it in the way that they want to use it, right? So in the end, we have this dynamic schema thing because the users want to use it differently than the way that we imagine than we imagine they would use it. And so this allows for flexibility in use case. This allows for more usability, not necessarily easier usability, more customization, and just a broader set of use case and a better user experience. Is there a publicly available product roadmap for Milvus? Christy, I don't know if you know this one. If you know this one, please drop it in. I don't know this one. How do you compact or delete obsolete or updated data in Milvus? Great question. So right now, this is why we have the IDs, right? This is why we have the ID field, basically. So you can grab your data and you can delete it and you can re-upsert it. So we just added this thing called Upsert, actually. So that's a new feature in Zilliz, as now you can just upsert your data like this. But the way that deletes were working before is that we would do a soft delete. So it's essentially, we store your data. So all data is stored kind of like, in bits, right? So what we do is we have a bit at the beginning. And in order to delete, we do a soft delete where we just flip the bit. And so this makes data recovery easier. And then later on, we can do a hard delete down the road. And once you do a hard delete, then there comes a likelihood that the segments that you have, the originally 512 megabyte segments, are no longer 512 megabyte segments, and some of them may be small. So after we do those deletes, what we'll do is every so often, and I believe this is up to user configuration, at least with Milvus, with Zilliz, it is automated for you. You can combine all these segments and re-index just small segments at a time. So this is still a computationally expensive task, but it's much less computationally expensive than re-indexing your entire data set, right? So as you delete more and more data, you get sparser and sparser segments. At a certain point, we'll say, I think it's maybe like 10, 20%. We'll just say, hey, we're going to combine these segments and we're going to reindex them. So at a certain point, they will get reindexed. But originally, the delete is a bit flip, and then later on an actual overwrite. What does auth 0? Oh, let me see. This is wait, I'm going forward. I meant to go backwards. Auth 0 LDP. Let me see where this is. What? Where is this? Is it in the other one? Is it in here? Yes. Oh, okay. I don't yes. Thank you. I did not realize that it was about this slide. Okay. I don't believe that it's auth 0. I believe that this is called auth O. I'm not entirely sure what this is, to be honest. This is part of the Zilliz Cloud stuff. I will get back to you on that. I will find the answer for you, and I will get back to you on this. I'm much more familiar with the Milvus side of things than the Zilliz side of things, as you might be able to tell. But yeah, so essentially, Zilliz will handle a lot of the authorization stuff for you. And I believe what this has to do is, I believe this is related to the role-based access control kind of stuff, right? Is when you are building these systems, you need to make sure that there are the correct authorizations, and that's what this is for. Auth 0 is popular. Yes, I know of auth 0, but I don't believe this is auth 0. It could be. We do allow you to sign up with GitHub and Google and whatever. So so the way that Zilliz works, so this is the Zilliz architecture. This is essentially how we're also able to do a decoupling of the control plane and the data plane, right? So essentially you have your private cloud, your VPC, right? We can do VPC tunneling. I think we can do VPC tunneling. It is definitely available to enterprises. It may not be available to the general public yet. But this right here is basically saying like, hey, we're going to take this Kubernetes agent, and the Kubernetes is going to handle like what's going on with our proxies, right? The load balancing and all that shit. And then we're gonna use that to run Milvus. We're gonna use Kubernetes, Helm charts, whatever, to orchestrate Milvus. Kubernetes is like your orchestrator, Milvus is your engine, right? And then you know, if you have a VPC with whatever you have in there that needs to happen, we can do the peer linking, and you can run that in your VPC. Oh, more questions. Unless they meant an IDP, an identity provider. Yeah, I don't know. I just don't know the answer to this question. I will find the answer to this question, and I can get back to you about it. What just happened? Oh my God, having more technical details. Okay, here we go. So yeah, these are the ways that you can use Zilliz. There's a starter tier. This is a serverless tier. This is free. Free for as long as we exist as a company. At least that's the current initiative. That's the current guideline for this. And this allows you to get 2 collections of up to 500K 768 dimensional vectors, or 256K 1536 dimensional vectors. The reason why we kind of set it up this way is because it's easier for people to grok like number of vectors and like size, as opposed to doing something like you know, half a CU, 1 CU, or something like that. We don't provide any uptime SLAs. Single availability zone. There's only GCP for this. We don't promise anything for security. And the main support that you get on the starter tier, the serverless tier, the free tier, is that you can come to the community and ask the community for support. And we have a Discord channel that is you know, for community support basically. And then you have the standard tier. This is the dedicated tier. This is the, you know, production ready. And this allows you, we have cost optimized, storage optimized, performance optimized. We have different tiers basically that you can use for this, and they all have different costs, and they all have different use cases essentially. And you can put however much data you need on here. And this comes with all like the basic security stuff, right? Data encryption, role-based access control, SOC 2, whatever. And you can get email support, and up to 2 technical people from your company can come and we'll answer questions from them. And then we have the dedicated enterprise tier, which is when vector databases are a part of your company's mission critical, is mission critical for your company. If your use of similarity search, if your use of being able to compare unstructured data is critical to driving revenue at your company, that's when you would use an enterprise kind of tier. And so here we have, once again, the same kinds of options for the for performance, but we also provide extra SLAs like 3 nines of uptime, multiple availability zones, the VPC private link, the data backups, and up to 4 contacts. And your organization can use multiple clusters, types of clusters if you need. What is the overhead to move from a serverless to dedicated cluster? I don't think it's anything. I think it's actually very. I don't think you experience any disruption in. I think you like literally you should not experience disruption in service doing that. Are the HTTP metrics usable by visualization tools like Grafana, Tableau, and D3? Yes. In fact, this morning I got a message that Tableau is just integrated into Zilliz Cloud. So the answer is yes, you can do this. And Grafana is also available. Can you manage your Milvus database using IAC like Terraform or a CLI? Yes, you can. Wait. Terraform. I'm not entirely sure. I'm not terribly familiar with Terraform or Ansible. But with the Kubernetes stuff, definitely. The way that I manage my non-Milvus Lite database is through Docker Compose. And that's just because I'm not working with something that is incredibly huge. I mostly use this for proof of concepts, MVPs, like that kind of stuff. But the Helm charts is how I see a lot of enterprises like Salesforce and AT&T using Milvus. So there are 3 types of CUs on Milvus. One is optimized for cost, which is basically, you don't need the best performance, but you need it to work, and it should still beat out the performance of other. It does. If you look at the benchmarking, you can bring your own data and always test it yourself. But if you look at the benchmarking, it does beat out pretty much the performance of most of the other vector databases out there. And this allows you to do 1 CU is 3.75 million 1024 dimensional vectors. When you go to storage, same difference. But when you get to performance, we are actually the storage, you get less storage on it, but that's because it is more compute heavy. It is meant for faster, for less latency and for better throughput. Oh, there's more questions. Somebody just has to create a Terraform provider to allow it to find and manage things like Milvus. Maybe Zilliz is working on one. Christy Sachi, I don't know if you know the answer to this one, but I don't. It could be. I think that we are interested in this space, and so we will definitely be moving towards allowing more flexible usage and allowing and trying to build the best user experience possible. Pulumi is the other popular IAC product. Okay, thank you. I haven't heard of this. If Milvus has an admin CLI, you can do your own scripting that way. I think that it does actually exist. There is like a CLI. I mean, so you can interact with Milvus through gRPC or through REST. And so I believe the CLI. I think you can just I think you can do that with the CLI. I don't see why that would be an issue as long as you can send all of the parameters that you need. Did I cover the rest of this? Performance is a lot faster than either of these. I think these are all the same. Here, example use cases. This is probably good for you guys to know. So data labeling or deduplication or clustering or outlier detection. Essentially, if you want data cleaning, data analysis, cost optimized is the way to go. Storage is for more of like, you want to compare many things. You have a lot of things, but you don't need to do a lot of comparisons. Or you need to do small comparisons, but what you really care about is being able to store a huge amount of data. That's when you would use storage optimized. And then for performance, you want more real time, more speed, more throughput, all this kind of shit. That's when you would use the performance optimized stuff, Gen AI, recommendation systems, chatbot, fraud detection, right? Real time, like real performance critical use cases. So as I was saying earlier, right, we are not just for RAG. RAG is just something that's very popular right now. The LLMs have brought in a lot of attention to vector databases, but really it's actually not the only use case. And I would say it's not, I don't even think it's going to be the biggest use case. Because really, like, things like drug discovery and product recommendations are huge. Inventory management, right? Fraud detection, like banks, they need to be like, like I had my credit card stolen like a couple weeks ago. And so like things like, and like, things like this is why it's important to have these ability to compare this unstructured data, like across not just, it's not just something that you feed into LLMs, right? It's something that you want to be able to work with because you're doing a similarity search thing. Relational databases can have indexes on commonly accessed columns for acceleration. Is there something similar to this for vector databases? I'm going to need you to expand on this question. Like, you mean like caching? We do have a tool called GPT Cache that does semantic caching. It's a semantic cache at scale. What's the query language for Milvus? The query language for Milvus is it's not SQL. Essentially, what you do is you provide a vector, and then it does a vector search. And if you need to do filters, you provide an expression, and it does an expression search. So I think I might have an example for this pulled up. I'm not sure if I have this pulled up. Where are my Visual Studio Code? Basic usage. Okay, so I'm going to stop sharing this and I'm going to share my VS Code. Share screen. VS Code. I believe this talks about this. Yes. Okay. So this is what a raw search in Milvus would look like. I will zoom in for you to see this. So essentially what we're going to do is you send in some embeddings, and then you tell it what field to run the approximate nearest neighbor search on. And you give it some parameters for the search. And so in this case, we're giving it L2 because that was what we stored it with. And then how many of the... Oh, so this is specific to the fact that we store this using IVF, which is inverted file index, which creates a list of a list of centroids. And this is just telling it how many centroids we want to search. Limit is the number of results we want back. And then output fields, this is where I was talking about the metadata, right? If you need this metadata, you pull it back. If you don't care about the metadata, you don't pull it back. So in this example, I'm only pulling back these two metadata fields, but what actually happened is this is what the actual fields look like. So I'm storing a ton of metadata and I'm only pulling back two fields. And then there's an expression here, right? A filtering expression like I was talking about. And this is how you filter expressions. It's kind of like SQL, I guess. The expression fields you can think of as like SQL, right? Like there's the same like kind of like greater than, equal to kind of stuff to it. So search language is API by SDK. Okay, I don't know what that means. Oh, can you expand on a use case such as the credit card being stolen? Dude, no, my credit card was literally stolen. I'm not using this as an example use case. It just was stolen. Why not use an LSTM model to identify fraudulent transactions? Where would the vector store come in? So LSTMs can't identify fraudulent transactions. LSTMs are meant for sequence transformations. And a vector store is able to do similarity search. And so the way the fraudulent transaction would be done, I guess, would be that you have like the information about the user, and you're vectorizing that information. And then you compare that information to the other vectors, right? So every time that there's a transaction, there's a lot of information about that transaction. And so you vectorize that information and you compare it to the other transactions for that user, and possibly also other like things the user is doing. So for example, if most of my spending is in Seattle, and then suddenly I'm buying something in Ohio, red flag, right? And you can see that in the vector distance. So things like that are basically how fraudulent detections are done. You see something that's unusual, out of the ordinary, and it does that. So the way this was being done before was actually through this thing called collaborative filtering. Collaborative filtering was for product recommendations, but similarly, you could do something like this with anomaly detection. Yes, it's vector distance, not an AI model. We're not using AI to calculate that. It's actually much simpler and much quicker to use vector distance. Now you do have to use a machine learning model to vectorize your data, but beyond that, it's simply the vector distance. We don't use we don't run it through some sort of model, basically. Okay, wait, where's my screen? I'm gonna stop screen share because I don't know where my screen is anymore. Okay. Okay, were there any questions here? Oh, there's some. So we're at time. So I'll answer the last few questions, and then if you have other questions, my name is in the corner. Just feel free to reach out to me on LinkedIn, or Christy, can you post the Discord link? And you can also feel free to reach out on Discord. This one's done. I'm guessing that because the schema and usage for vector structure and usage is so different from databases like SQL, there's no practical way to create an index, something like an index for relational systems. So I talked about this earlier, the indexing. We do an index, right? And so the indexing is the way that we access your vector data, is the way we compare your vector data. And it's not so much that the index is done caching or whatever. The indexing is much more of something like, you have 6 billion vectors that you want to search on, but you don't want to do 6 billion comparisons. And so you create an index over that. And indexes, examples of indexes are like IVF, inverted file index, where you create a ton of centroids. And then the way that works is first you search for just the centroids. And based on the centroids, you can pick out what might be the closest one. So you reduce your vector space that you have to search by a lot, and you reduce the amount of computations that you have to do. Other examples of indexes include like HNSW, hierarchical navigable small worlds, where essentially every layer is a sparser and sparser graph, and then you search the top graph all the way down until you get to the bottom. And in this graph, we encode all the distances so you don't have to do as much of the calculations. So we have an index. And in fact, indexes are almost required, necessary for vector databases, because if you don't have them, you're just going to be doing flat comparisons. And the best computational, like the best, most computationally optimized systems will still be slow for that. So there is an index. It doesn't work the same way that it works in relational systems. Essentially what it is it's not just an efficient way to access your data. It's pretty much the only way you can really work with it at scale. Okay, thank you guys. And H. Kraus, I believe we've met before, so hope to see you at one of our Seattle events again soon. Thank you guys, and have a good day.